We talked before in the previous video about the acidity of alkynes. And here the pKa of terminal alkynes is about 25. So let's see, here we're going to be studying what bases we need to use to remove the hydrogen in the interest of making the alkynate anion, and so that we can use it later in synthesis. So I'm interested in investigating what type of base do I need to use here. And say, I'm going to put an anion, but let's see, what type of base? What is the base that I will need to use to form the anion that I'm interested in? So acid base. So here you will have your conjugate base, and of course, they say BH here, deprotonate. If this was negative, this will have no charge, of course. So conjugate base, conjugate acid. All right, so what type of base would work? And here we're going to be analyzing the equilibrium. Say that I want to do this, and I want to see if ethoxide will work. So I'm going to draw that again. My terminal alkyne as my acid, and say that I make it react with ethoxide. And when I do that, then again, my acid-base reaction, let's use little arrows showing the mechanism. Acid-base, so the proton transfer. So here you will have your conjugate base, and your conjugate acid is ethanol. So how do I know if that works in that direction? Let's analyze the pKa's of the acids. We said that the pKa of the terminal alkyne is 25. The pKa of ethanol is 16. So if we analyze the pKa, we see that ethanol is much stronger acid than the alkyne. And so, and always the equilibrium favors that weaker acid. So this is a weaker acid, so this reaction will not work. So I am going to draw pretty much the arrow. The big arrow is in this direction, and a small in the other direction. So pretty much not even an equilibrium, because the difference in pK is so large that this reaction will not work. So let's see, and now I'm going to try a different base. This time I'm going to use sodium amide. This is again my terminal alkyne. I know my pK is 25. And when I use sodium amide, well, I'm not writing the counter ion. So sodium amide, but it's what we use. But I'm going to use just right here the amide anion, right? So that's that. So if I do that reaction, what would be the product? Still, I don't know where this is going. It would be reactant favor or product favor. But what I know is that's my base. I'm getting this hydrogen. I'm forming my conjugate, my paraconjugates. Same here, my alkynate anion, here terminal. And I am forming ammonia. Now, for that reaction, again, we need to see if it works, creating the anion that I'm interested in. Again, I want to form the alkynate anion because later we're going to be using that as nucleophile in some reactions. But will this work and make that? Well, again, we're going to be comparing pKa's and the equilibrium, whether this reaction is product favor or reactant favor depends on the strength of the acid, the relative strength. So here, pKa is 38. So clearly, when you see those numbers, remember that the larger the pKa, the weakest the acid. So weaker acid is ammonia compared to the terminal alkyne. So this is actually a reaction that's very much product favor. Notice the large difference if you do 38 minus 25, not. So this is not even an equilibrium. This reaction proceeds to product formation and is very useful. So that is one base that we're going to be sodium amide. That's the with a counter ion, right? that we're going to be using to deprotonate alkynes in synthesis. So in summary, if we're selecting a base to deprotonate the alkynes, we need to select a base like that, where you see that the conjugate acid has this number, here's a pKa larger than that. It needs to be larger so that the reaction favors product formation and goes that way. Here we were comparing ethanol and the alkyne, and we saw that this pKa is larger, so that's a stronger acid. The weaker acid is that, so the reaction was not favored in the product formation. In fact, it goes to the reactant side. So we need to be using this type of base.